So, History of Mathematics, Lecture 9. We're going to begin the chapter on Heron's formula. And I think that the first exam, which is on campus, live in person, Gillette Hall, will be on Monday, March 11. And it will cover these first 5 chapters in the text. So the exam covers chapters 1 to 5 in our book, Journey Through Genius. So this is almost all about geometry. So and after chapter 5, we'll be doing algebra, a little bit of calculus, a little bit of set theory, a little bit of number theory. But the first 5 chapters are on geometry, and that's what the first midterm exam will cover. There'll be a second midterm exam that will be based on chapters 6 to 10, obviously later in the semester. And then we'll cover after that 2 more chapters, chapters 11 and 12, and the final exam covers everything. Okay. Any questions about this? So in chapter 5, the great theorem is Heron's formula for the area of a triangle. Let me just say a word or two about that, and then I'll come back to it later in this lecture. There's more in chapter 5 than just Heron's formula, but if you have a triangle and the sides are, I don't know, A, B, and C, and the height is h, the area, A, is half the base times the height. So if you know the base and the height, you can find the area. So let's say I give you a triangle where not really drawn to scale. Say this is 17, this is 25, and this is 26. What is the area? Well, you know the triangle, 3 sides of a triangle uniquely determine the triangle. Every triangle with these 3 sides is congruent to every other triangle with sides of the same lengths. So the area is well defined, but what is it? Well, you have to know, if you want to use this formula, you have to know the height. The area is half the base times the height. But for this triangle, what is the height? And the answer is, you don't know. I mean, there may be some sophisticated way to calculate it, but you don't know. So that means for a simple triangle like this, you can't find the area. So we have this formula, but it's not always useful. Now, if you look at this triangle, if you know the sides, you know the perimeter, P, which is the sum of the lengths of the 3 sides of the triangle. Let's see, this is 42, I think this is 68. And in Heron's formula, what one uses is not the perimeter, which is easy to calculate, but something which is almost as easy to calculate, which is called the semi-perimeter, S, which is half the perimeter. So this is 68 over 2, which is 34. And Heron's formula says the following. If you have a triangle, you know the three sides. So for this triangle, the semi-perimeter, S, is the sum of the sides, the perimeter A plus B plus C over 2. And the area is equal to, and this is the magic formula, the square root of S times S minus A, S minus B, S minus C, where these A, B, and C, that's what you know. Those are the three sides of the triangle. So in Heron's formula, you only need to know the three sides of the triangle and you can calculate the area. So for example, for this triangle, the area A is the square root of the semi-perimeter, 34, times S minus A, 34 minus 17, S minus B, or S minus B, 34 minus 26, S minus C, 34 minus 25. So that's the square root of 34 times 17. 34 minus 26 is 8, and 34 minus 25 is 9. Let's see if I can calculate that without even using my calculator. Let's see, 34 is 2 times 17. Times 17, that's 17 squared, times 8, which is 2, times 4, which is 2, makes that 2 squared, times another 2 squared, 4, times 9, which is 3 squared. Oh, so this turns out to be a perfect square. This is the square root of what squared? 4 times 3 times 17. So that is 4 times 3 times 17. So that's 12 times 17. Let's see, what is 12 times 17? 100 and, is that right? Something doesn't seem to be right. 2 times 2 is 4, times 3 is 12, times 17. 12 times 17. $34. 34 minus 17, 34 minus 25, and 34 minus 26. So that's 34 times 17 times 8 times 9. So that's 17 times 2 times 8. So that's 17 times 16. 17 squared, 4 squared, 3 squared. So I get 12 times 17, which is 154. This is an example from the book. The book gets a different answer. So if I get an answer and the book has a different answer, I assume the book is wrong. Unless someone can tell me where I made a mistake. In any case, this is Heron's formula. It really is a beautiful formula because it solves the problem of determining the area of a triangle from the simplest things you know about a triangle, which are the lengths of the three sides. Okay. So we'll come back to this, but this is the Heron's formula, which you have to know. Right? I mean, very likely going to be a question on the midterm. I give you a triangle and I ask you to calculate the area. Any questions about this? This is the great theorem in this chapter. Okay. Heron lived 200 or 300 years, 200 years roughly after Archimedes, and Archimedes was certainly the greatest mathematician of Greek times. There was a contemporary of his, a mathematician named Eratosthenes, who was sometimes called Eratosthenes II, because he wasn't the best mathematician of his time, he was the second best. And he was also a physicist, but he wasn't the best physicist of his time, he was the second best. And he was also an astronomer, but not the best astronomer of his time, he was the second best. So sometimes he's called Eratosthenes II. And there are two very important things, he did many things, but two of the most important things he did are described at the beginning of chapter 5, which are the following. There is what is called the sieve of Eratosthenes, which is used to compute prime numbers, primes, up to some point x. And the second thing he did was he computed. Now, sometimes they tell you in school that Columbus proved the earth was round because he sailed west from Spain. He thought he would get to India, but he came to America, but he was trying to prove the earth was round by sailing west and coming and getting to Asia. But of course, the Greeks knew that the earth was round. The Greeks knew that the earth is round. By that I mean that it was roughly a sphere. So the Greeks knew that. So the only question is, if you have a sphere, what is the diameter? Or equivalently, what is the circumference? So Eratosthenes computed the circumference of the planet Earth. I mean, this guy sitting in the middle of Alexandria, Egypt, was able to figure out, I mean, everyone knew, whatever that means, everyone knew in Greek times the earth was round. And if you know something is round, is spherical, you want to know how big a sphere is it? So what is the radius, or what is the diameter, or what is the circumference, or what is the volume? These are all equivalent geometrical facts, given the work of Archimedes. He computed the circumference of the earth, and I'll explain how in a moment. But then I want to discuss both of these things. So let's just recall a prime, or a prime number, is an integer p, at least 2, whose only positive divisors, that is, the numbers that when you divide them into p go evenly, they leave a remainder of 0. The only positive divisors are 1 and p. For example, p equal 13 is a prime. 53 is a prime. 101 is a prime. That is, if you look at all the possible, e.g., for example, if you look at all the divisors of 13, just 1 and 13. Positive divisors, -1 and -13, but we're only looking at positive numbers. 53. Try all the factors, all the numbers less than 53. The only ones that divide evenly into 53 are 1 and 53, 101. Okay. So that's what a prime number is. The other numbers are called composite. A composite number is an integer n, at least 2, that is not prime. So that makes it easy. Either a number at least 2 is prime. If it's not, it's composite. Or equivalently, n is composite if there exists a divisor, an integer d, such that d is strictly between 1 and d divides n. That is, n is d times q for some integer q. So that's what a composite number is. So for example, 14 is composite. 57 is composite. 1001 is composite. Why is 14 composite? Well, 14 is 2 times 7. So 2 and 7 both divide 14. 57 is 3 times 19. So 3 and 19 both divide 57, so 57 is composite. 1001 is trickier. I think 1001, if you multiply it out, is 7 times 11 times 13. Yeah. So these are composite numbers. Right? So a prime number is an integer bigger than or greater than or equal to 2. A composite number is greater than or equal to 2. What about the only other positive number left? N equal 1 is neither prime nor composite. So there are 3 classes of numbers, positive integers: the prime numbers, the composite numbers, and the number 1, which we say is not prime or composite. It's special, or it's just the number 1. But this is our convention. This is how we define these things. Sometimes in elementary school, they would tell you that 1 was a prime number, but that hasn't been done for a long time, and it's not the definition that anyone's used for a long time. Okay. Any questions about these definitions? Another good likely midterm exam question is to define prime and composite numbers. Certainly something about primes and composites will be on the midterm. So recall Euclid proved there are infinitely many primes. So you can't write a list that stops after a finite number of steps and includes all the primes. Can't be done. Problem. Find all primes P up to 1,000. So one solution, check each number, integer, up to 1,000. Like take the number 877, divide it by all numbers less than 877. If one of them divides 877, it's composite. Otherwise, it's prime. So this works, but it takes too long. This method or this algorithm is inefficient. It takes too long. A better solution, use something called the sieve of Eratosthenes, and which is based on the following fact. The fact is, if n is composite, that means it does have a proper divisor other than itself in 1, then n is divisible by an integer d. So how can you tell if n is composite? Divide it by all possible smaller numbers. But the observation of Eratosthenes is that if n is composite, it's divisible by an integer less than or equal to the square root of n. So let's say you wanted to find all the primes up to 10,000. So you take a number up to 10,000, you might have to divide it by all the numbers up to 10,000. But the square root of 10,000 is 100. So this observation of Eratosthenes says that if a number no bigger than 10,000 is composite, it's divisible by a number, and therefore divisible by a prime, less than 100. So you don't have to check all the numbers up to 10,000, you just have to check the numbers up to 100. And we know from Euclid, every number is a sum of a prime, is a product of primes. So in fact, if n is composite, then n is divisible by a prime p no bigger than the square root of n. So this is the key arithmetical fact that underlies the sieve of Eratosthenes. So let me show you how you convert this idea into an algorithm. So let's say I want to compute the primes less than or equal to, I don't know, I'll just say 80. So you start by writing down all the numbers. Maybe I'll make it 60 so I don't have to write so much. It's up to 30. So these are all the numbers from 1 to 60. If n less than or equal to 60 is composite, then n is divisible by a prime p, which is less than or equal to the square root of 60. And the square root of 60 is less than 8, certainly. So what are the primes less than 8? So if n less than or equal to 60 is composite, then n is divisible by a prime less than 8, 2, 3, 5, or 7. Right? So this is really the fundamental fact. Every composite number less than or equal to 60 is divisible by 2, 3, 5, or 7. So let's look at our list of numbers from 1 to 60. I want to find the primes. 1 is not a prime, so I cross it out. 2 is a prime, but every multiple of 2 is composite. So I can cross out all the multiples of 2. Right? Well, I mean, that's actually the easiest case. They're the even numbers. An even number bigger than 2 is certainly not a prime number. So I cross out all the multiples of 2. Okay. What's the first number I haven't crossed out? It's 3. That's a prime. But every multiple of 3 is composite, so I can cross out all the multiples of 3. 6, 9, 12, 15, 18, 21, 24, 27. Some numbers get crossed out more than once. 33, 36, 39, 42, 45, 48, 51, 54, 57, 60. The next number that's not crossed out is 5. That's a prime. But then I can cross out all the multiples of 5. 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60. The next number that's left hasn't been crossed out as 7. That's a prime. And then I cross out the multiples of 7. 14, 21, 28, 35, 42, 49, 56. So if I look at all the numbers up to 60, I've crossed out, I have 2, 3, 5, and 7, and then I've crossed out every multiple of 2, 3, 5, and 7, bigger than 2, 3, 5, or 7. Any number up to 60 that's composite has been crossed out, because every number up to 60 that's composite is divisible by 2, 3, 5, or 7. So the numbers that are left, it's like a sieve. We have sieved out the composite numbers. Any number that's left must be a prime. What numbers aren't crossed out? 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, and 59. So those are the primes. The primes less than or equal to 60 are the numbers that aren't crossed out. 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, and 59. That's it. So this is the sieve of Eratosthenes. And along with the Euclidean algorithm, this is one of the two great, if you like, computer programs that come from the ancient Greeks that are still in use today. And these algorithms are built into most computer software that you use. Right. Any questions about this? This is really an incredibly important and beautiful piece of arithmetic, piece of number theory, piece of mathematics. This is the sieve of Eratosthenes. It's a very computationally efficient way to calculate all the primes up to a given point. And in the text, you see an example of the sieve of Eratosthenes for all the numbers up to 100. So, but it's worth being able to do this kind of calculation. Okay. Now, I said that this chapter discusses two achievements of Eratosthenes. And the second was he computed how big the Earth was. I mean, so there's a book by Eratosthenes, which is referred to in later Greek literature, but has disappeared. It's called On the Measurement of the Earth. So here's the Earth, right? Compute the circumference. Now, you have to realize this would be like an unbelievably amazing feat if you could do it, right? I mean, how is this poor Greek guy who barely knows mathematics, I mean, who knows all the mathematics that was known at the time, but that did not include algebra, for example, at least not in the Greek world. So the computation is based on the following. So this is the Earth. And far away is the sun. And light, this is light. The sun shines and light comes from the sun and hits the Earth. And actually, the way I've drawn it, it's backwards because the sun is much, much bigger than the Earth. And you can imagine that these beams of light, when they hit any small region of the Earth, are hitting it sort of perpendicularly. Like these are like parallel lines of light, parallel light rays of light coming in and hitting the Earth. Now, so Eratosthenes lived and worked, he was Greek, but he lived and worked in Alexandria, Egypt. So somewhere on the Earth is the city of Alexandria. And a certain distance from, let me draw this a little bit better. So let's say here is Alexandria. And here is the sun, with the rays of light coming and hitting the earth. And it turns out, south of our Alexandria, there was a town called Syene. Obviously mispronouncing it, but I'll call it Syene. And what everyone knew was that on the first day of summer, light hit this town directly. It didn't come in at an angle, right? Like if light were hitting Alexandria directly, it would be coming in like this. But it's not. Light is coming in like this. But where Syene is located, light is hitting it directly. And the way they knew that was that there was a well. And at midday, on the first day of summer, the sun was directly overhead. So light would come in, go into the well, hit the bottom, and reflect out exactly as strongly, basically, as it went in. So the sun was directly overhead the city of Syene at that date, at that time. Right? So if you had a pole at this place, there would be no shadow, right? I mean, if the sun hit this pole at an angle, there would be a shadow, but it's coming straight on. There's no shadow over the town of Syene. But north of Syene, you could put a pole So here is this pole, perpendicular, it's like straight up. And now, when light comes in, it leaves a shadow. There's a shadow here. Right. And you can measure this angle, right? Because you have a triangle. You have this side, this is a right angle. You know this length. This is approximately a right triangle. So you can figure out what that angle is. And the angle of the shadow at Alexandria was measured by Eratosthenes to be 1/50th of the whole angle. Let's just say an angle of 360 degrees, or 2 pi radians. This angle was like 360 over 50 in degrees, or 2 pi over 50 in radians. So let me draw the picture as it is if you look at your book on page 116. It's like, here's the center of the earth. Again, the Greeks knew the earth was a sphere, it had a center. Here, for this point S, that's Syene. For this point A, that's Alexandria. And here you have, this is the sunlight coming in. This is the shadow. And this angle is 1/5 of the circle, 1/5 of a whole angle. So we have that, what is the circumference of the earth? So the distance from Syene to Alexandria, that part of the circumference of the circle, over the whole circumference is the same as the ratio of the angle for this angle alpha over the total angle. Well, sorry. The total angle is 1/50th of this. So the circumference of the earth is equal to 50 times the distance between these two Egyptian cities, Syene and Alexandria. And if you measure that distance, you get, well, there was a Greek measurement in terms of what are called stadies. As well as we can figure it out, knowing what these distances are, this is approximately 24,466 miles. So Eratosthenes, in using miles, which, I mean, the Greeks didn't measure in miles, but converting their distance, their length to miles, Eratosthenes determined the circumference of the earth was approximately 24,466 miles. And the figure that we use today, the true value, is about 24,860 miles. I mean, that's an amazingly accurate approximation. And the fact that 2,500 years ago, more than that, 2,700 years ago, Eratosthenes could calculate the circumference of the earth to an accuracy of 3 or 4 decimal digits. I mean, and the right order of magnitude, 2 times 10 to 2.4 times 10 to the 4th. I mean, that's correct. So hopefully you'll be impressed, and you have to actually read carefully this description and look at the geometry to understand exactly how, knowing the sun is directly overhead at a certain time at the city of Syene and at the city of Alexandria, a certain distance away that you can measure, the sun is not directly overhead. So when the sun shines against a pole that's standing straight upright at Alexandria, it makes a shadow. So you have this right triangle and a certain angle here, and that angle gives you the fraction of this as an angle of the whole angle is the same as the ratio of the distance from Syene to Alexandria to the circumference of the entire earth. I mean, that is a very impressive piece of physics, engineering, whatever it is you want to call it, but it's very good. Okay. All right. Let's go back to Heron's formula. You have a triangle with sides A, B, and C. The area, the semi-perimeter is A plus B plus C over 2. The area is the square root of S, S minus A, S minus B, S minus C. By the way, if you want to study dimensions, area has the dimension of length squared. S, A, B, and C, they're lengths. So this is a length times a length times a length times a length. So the dimension of what's inside the square root sign is like the 4th power of the length. And when you take the square root, you get the 2nd power of the length, or the square of a length. And that's exactly the right dimensions for area. So dimension analysis gives you this formula, makes sense. Also, it shouldn't matter what you label A, B, and C. I mean, what order you label them in. So the formula for the area should be symmetric in A, B, and C. And in fact, if you permute A, B, and C in any way, the sum of A, B plus B plus C doesn't change. So the semi-perimeter doesn't change. And these 3 factors might be permuted, but they're the same numbers, just written down in a different order. So the product is the same. So these sort of simple conditions for the correctness of the formula, necessary conditions, are certainly satisfied. So this is Heron's formula. And the proof uses geometry, Euclidean geometry. So I'm going to start the proof today, but not finish it, I suspect. And we'll finish it next Monday. So there's several propositions we need in the proof. The first says that the bisectors of the angles of a triangle meet at a point inside the triangle that is the center of the triangle's inscribed circle. So in any triangle, there always is one and only one circle that can be inscribed in the triangle, which is tangent, touches in exactly one place all 3 sides of the triangle. And that circle has a point which is called the incenter. So the center of the triangle's inscribed circle is called the incenter of the triangle. And this proposition says that if you take any triangle and you bisect the angles, these angle bisectors intersect at a point, and that point is the center of the inscribed circle. So let me just check, maybe try and draw this a tad better. Here's the triangle. Now, I'm just doing this very crudely, but in Euclidean geometry, there's a straight edge and compass method to construct the angle bisector of any triangle, of any angle in a triangle, of any angle. So let's say these are the angle bisectors. This point, I claim this point is the center of the inscribed circle. Well, it's really bad trying to do these things by hand, but it's really bad. But I'll start again and draw another picture. Maybe I'll make it easy. I'll start with a circle. And okay. So let me call this A, B, C. And here I have a triangle, ABC, and an inscribed circle. And from the center of the circle, this is the incenter, I draw lines to the three vertices of the triangle. And I claim these lines are the angle bisectors. Let's see. Why is that true? Well, the points of tangency, where the circle is tangent to the three sides, that's one. That's one. Okay. So here we have a triangle, ABC, with an inscribed circle. Those I call these points D, E, and F. So the circle is DEF, And the incenter is this point 0. Now, if I look, for example, at these two triangles, triangle OEC, that's this triangle, and triangle ODC, that's this triangle. If you look at these two triangles, these are right triangles. The side OE and the side OD have the same length because they're radii of the circle. And the side OC is equal to itself. That's the hypotenuse of this triangle. So you have two right triangles with sides and hypotenuse equal. It means these two triangles are congruent. Triangle OEC is congruent to triangle ODE. So if I call this angle 1 and this angle 2, angle 1 equals angle 2. Because these are corresponding angles of congruent triangles. So OC is the angle bisector of angle C. This line bisects angle C. That's the angle bisector. And similarly, if this is angle 3 and this is angle 4, these two triangles, triangle OEA is congruent to triangle OFA. So angle 3 equals angle 4. And OA, this line, bisects angle A. If I look at these two triangles, call this angle 5 and this angle 6, triangle OEB is congruent to triangle ODB. So again, they're right triangles. The short sides are radii of the circle, so they're equal. They share the hypotenuse. So angle 6 equals angle 7, and OB bisects angle B. So these are the angle bisectors. They meet at a point inside the circle, which is the incenter, sorry, inside the triangle, which is the incenter of the triangle. Okay. That's the first proposition that we need. There's a lot of geometry that is going into Heron's formula. Next. Proposition 2 says in a right angle triangle, if a perpendicular is drawn. So let's draw the triangle. Like this. So this is my right angle triangle. And think of this hypotenuse as the base. Maybe this is A, B, and C. That's the right angle. In a right angle triangle, if a perpendicular is drawn, from the right angle to the base, so that's the perpendicular that I'm drawing. Call that M. The two triangles on each side of this line AM are similar to each other and to the whole triangle. So let's recall, triangles are similar if they have the same angles. So for example, for this original triangle, triangle ABC, what are the angles? We have angles A, B, and C. A is a right angle. Suppose we look at triangle MCA. So in this triangle, angle AMC is a right angle, so it's the same as A. Angle C, which is MCA, that's angle C, that's the same. What's the third angle in this triangle? The third angle in this triangle is angle CAM. That's that angle. So this angle plus this angle add up to a right angle, because they're the two acute angles in a right triangle. In this big right triangle, this and this add up to two right angles. So this angle is complementary to C, and this angle is complementary to C. So angle CAM is equal to angle B. So in this little triangle, the three angles are equal respectively to the three angles in the whole triangle. What about this larger triangle on the right? That's triangle MBA. So in that triangle, angle AMB is again a right angle, so it's the same as angle A. Angle ABM, that's this angle, that's just angle B, that's the same. And what is the third angle? The third angle in this triangle is angle MAB. Angle MAB is this angle. Now this plus this add up to two right angles. And this plus this add up to two right angles. So this angle has to equal angle C. So these are equal. So we have a right triangle. We drop the perpendicular from the right angle to the hypotenuse. That divides the right triangle up into two smaller triangles. So those two small triangles and the original and whole triangle are similar to each other. That's proposition 2. There's a lot of geometry in the history of mathematics. Well, 5 out of 7 chapters for us. Sorry, 5 out of 12 chapters. What's proposition 3? In a right triangle, so this is a right triangle. Label the vertices A, B, and C. Here's the hypotenuse. Take the midpoint M. So in this case, in a right triangle, the midpoint of the hypotenuse is equidistant to the 3 vertices. Well, proof. First, M is the midpoint of BC. So the distance from M to B equals the distance from M to C. That's just definition of midpoint. I have to show that the distance from M to A is the same as the distance from M to B and C. So must show the distance from M to A is the same as the distance from M to B, or the distance from M to C. We know these two are equal. We have to show that this distance is equal to that. So from this point M, draw the perpendicular to the side AB. Actually, let me do it slightly differently. Here we have our right triangle, ABC. Let D, and I could do it the way I started, but I want to do it the way it's done in the book, so when you're studying it, it's easier to understand. Let D be the midpoint of AB. So this line and this line are equal in length. Then construct the perpendicular to AB at D, and let M be the point where this perpendicular line intersects the hypotenuse BC. Drawing this line, this is perpendicular, and this point is M. Now, consider the triangle BDM and triangle, this little triangle, ADM. So these are right triangles. These sides are the same. They share this side. So by side angle side, these are congruent. So MA equals MB. And this angle, MAD, equals angle MBD. This angle equals that angle. This also follows from the fact that triangle ABM is now, we know, is isosceles. So this angle equals this angle. It's the same thing. We can do this at the next step in different ways, but let me just follow the way the text does it. Suppose I look at angle ACM. Angle ACM plus angle, that's angle B plus angle C, are the two acute angles of a right triangle, so they add up to a right angle. So angle ACM is equal to a right angle minus angle B, angle ABC. This angle is equal to a right angle minus this. But this is the same as this. So this is the same as a right angle minus angle MAD. And a right angle minus angle MAD is this angle. That's equal to angle MAC, which means this angle equals this angle, which means triangle AMC is isosceles, two base angles are equal, which means that this side equals this side. MA equals MC. So we have MA equals MB equals MC. So this point is equal, if you take the midpoint of the hypotenuse, it's equidistant to the three vertices of the triangle. Okay. I'm going to prove two more propositions, and then we'll stop and finish the proof of Heron's formula on Monday. So I just proved propositions 1, 2, and 3. So the next must be proposition 4. So you have a quadrilateral just any four-sided figure, OABC, and the proposition says the following: if actually, Let me label it the way the text does. So this is labeled H, and this is labeled B. So I have a quadrilateral if AHBO is a quadrilateral. Quadrilateral, 4 sides, is any figure with 4 edges as its side. If AB is a quadrilateral with diagonals, AB and OH. So let me draw the diagonals. Here's AB. There is OH. And if the angles HAB so I want HAB, I want this to be a right angle. However badly I drew it, but that's a right angle. So if HAB is a right angle, and HOB, which is HOB, if this is a right angle, then a circle can be drawn passing through the vertices of the quadrilateral. So this is a kind of a strange proposition. You have a quadrilateral, OAHBO. You draw the diagonals, and if one diagonal makes a right angle with a side, and another diagonal makes a right angle with a different side, then you can circumscribe a circle. You can draw a circle that passes through the 4 points of this quadrilateral. Another way of saying that is, so this is equivalently, there is a point, let's call it M, equidistant to A, H, B, and O. Because if you had a point M, the same distance from those 4 vertices, just draw the circle with center at M and radius equal to that distance, and it will pass through those 4 points. So proof. Bisect the line BH at M. So this point M, which is the bisector of BH, that line, I claim is equidistant to BH, A, and O. Well, of course, M is equidistant to B and H because it's the midpoint of that line. Now we have a right triangle ABH. M is the midpoint of the hypotenuse. That's a right triangle. M is the midpoint of the hypotenuse. Implies M is equidistant to the vertices of that right triangle. So the distance from M to A is the same as the distance from M to B and M to H. But now this is also a right triangle. We have a second right triangle, OBH. M is the midpoint of the hypotenuse, BH. So the distance from M to the three vertices of this triangle are equal. So MO equals MB equals MH. So by the previous proposition, this point M is equidistant to the four vertices of the quadrilateral, and we can inscribe a circle around the quadrilateral. So what is called a cyclic quadrilateral, a cyclic quadrilateral is a quadrilateral inscribed or inscribable in a circle. So if you have a quadrilateral that satisfies this curious condition, it's a cyclic quadrilateral. And then the last proposition that I will prove today is, this is proposition 5. The opposite angles of a cyclic quadrilateral sum to two right angles. So we have a circle. We have a quadrilateral inscribed in the circle. And if you take the opposite angles of this quadrilateral, they add up to two right angles. So this was actually proved in chapter 3. This was proposition 322. So let's just review that proof. We have A, B, let's make this A, B. This D and this E. So here we have the cyclic quadrilateral, A, B, D, E. And we draw the diagonals, AD and EB. Let me label this the way I started to. This is ABCD. And we draw the diagonals AC and BD. So proof. Draw the diagonals AC and BD. So we have a triangle ABD. And let me call this angle 1 and this angle 2. So angle 1 plus angle 2 plus angle A. Those are the interior angles of a triangle. These add up to 2 right angles. And let me call this 3 and this 4. I'll call this 3 and this 4. So angle 3 and angle 4 3, 4. Okay. Yes, this is very good. Let me draw this picture again just to try to. This is A, B, C, D. And I draw this diagonal, call this A, angle 1, and this 2. So angle 1 plus angle 2 plus angle A, those are the interior angles of a triangle. They add up to 2 right angles. Let me draw this diagonal and call this angle 3 and this angle 4. Now, here's angle 3, and angle 3 cuts out this arc of the circle. So angle 3 is an inscribed angle on the arc from A to D. But if I look at angle 1, this is angle 1, it cuts out the same arc. And 2 inscribed angles that cut out the same arc are equal. So angle 1 equals angle 3. And similarly, if I look at angle 4 is this angle. It cuts out that arc. But angle 2 cuts out the same arc. So angle 2 equals angle 4. So I have two right angles are equal to angle 1 plus angle 2 plus angle A, but 1 equals 3 and 2 equals 4. So this is angle 3 plus angle 4 plus angle A, and 3 plus 4 add up to angle C. So angle C plus angle A add up to 2 right angles. Those are opposite angles of the quadrilateral. That's the proof. Okay, now so we actually covered a huge amount of material today. There's a lot to learn, a lot to study. We studied 2 results of Eratosthenes. The one you really have to know, because it really is purely mathematical, is the sieve of Eratosthenes. I described Eratosthenes' calculation of the circumference of the Earth, but that's a little bit too far from the mathematics I want to deal with in this. So that I wouldn't worry about so much, though it's extremely interesting. But you absolutely positively do have to know the sieve of Eratosthenes. And then we started the proof of Heron's formula. And I will finish the proof next Monday. Monday is the 4th of March. Wednesday of next week will be a review session for the midterm, and the midterm live on campus is Monday the 11th, so just a tad less than 2 weeks from today. Okay. That, well, with all the geometry we did, that's where we are. Any questions about what we've been doing? There really is a lot to learn, and I strongly encourage you to come to Zoom sessions. There's one tomorrow at 7, one Friday afternoon at 4:30. And if you have questions and can't make either of those, send me an email and we can set up a time that works for you. Okay. Any questions before we're done for the morning?